Okay, well, it's 3:30, and I guess I'll just go ahead and get started, because it is Friday, and there's only so much, like, hanging out at work you want to do on a Friday evening, right? Never mind, right? This is the only place any of us ever want to be. Sweet, sweet College of Sciences, GMCS. Fun. I'm Chris. I'm in the math department. If you don't know me, which I should actually assume that. It's weird, right? This whole like coming back from lockdown, right? Like usually by this point, I've just run into everyone over the last year or two, but some of you may well be almost done with your degree and have no idea who I am, which is, you know, just the way it went, right? So today I'm going to be talking about dynamic mode decomposition, dynamical systems, multiple and missing scales, and learning dynamics. I got a little ambitious. The multiple scales I'm probably going to have to elide over, because by the time I was done, I was like, "Ooh, this is getting to be a long talk." Because I haven't spoken in CSRC in a while, and I always kind of feel obliged to like kind of tell people like, what have I really been up to, because it's kind of like, you know, talking to like my fam. And so I kind of started putting everything I've been up to, especially with Jay there over the last couple of years. And it's been a lot. Okay, I'm pressing buttons and it's not going. Base? No. Does it have to be clicked on? Is that it? Okay, fine. Great. So yeah, the immediate collaborators and all this work. Oh no, that's going to cause a migraine. So look at that. Actually, can that stop? Or is that just the way that works? Does everyone see the? Okay. I have optical hallucination migraines, so sometimes I actually can't tell what is or isn't in front of my eyeballs. And it looks pretty much exactly like that. That's terrible. Yeah, that's scaring the shit out of me, actually. So if I don't look at the screen, it's because that needs to stop. So yeah, anyway, collaborators, Jay there, of course, you know, Alex Eiler at UC Irvine, and then Paul Hassan worked on a lot of this. She was an undergrad here at SDSU, and then got into a bit of a bidding war between various PhD programs, and then ultimately decided on UCSD mechanical engineering to work with someone who's doing data science there. So hopefully that kind of covers it a little bit. Okay. So data. We hear about it all the time. Certainly relative to someone like me who finished their PhD around 2009, the word data was starting to get thrown around. And then all of a sudden, over the next handful of years, it just was all anyone was talking about. And if you weren't doing data science, then you weren't doing applied math. And at first I was a little like, fad. And then over time, I'm like, no, I just didn't get it. And so this is, I think, a really cool slide to hang out with for a minute. Now, we're not going to be talking about any of the data represented here, but this gives you an idea of the scale of what's been going on in history over the last century. So a data set that was big back in, say, the turn of the 1900s, right, was on the order of a couple thousand entries, right? That's big in the 1900s. And then you can just see as time goes on, there's this little doop and then boom. And we have now crossed 6, almost 7 orders of magnitude in what we consider a data set to be. You know what I mean? In about 100 years or less, we've crossed 7 orders of magnitude, right? So it doesn't even matter what these represent, mostly images, maybe some statistics around various like industries, I think like sports statistics, for example. Moral of story, right? What we're dealing with, what we're thinking about is just scales and scales bigger than anything we've ever thought about at any prior point in history. Which is to say, when we talk about machine learning, and yes, some of it is, you know, hot topic, right? Kind of faddish, some things will come, some things will go, obviously, but there's no getting around the reality that it's here to stay. And that a lot of us are going to be trying to think about over the next handful of years, how do we start using it in interesting and compelling ways in areas where maybe it hasn't been employed as much. And that's definitely been my research focus over the last couple of years. So data for me is going to be time series and multidimensional time series. So just sequences of vectors where the idea is I get a different vector as I wait around in time. And we'll get into more details here in a second, but generally speaking, I think of these as being uniformly sampled. They don't need to be that necessarily, but they will be in my case because it just makes things easier to explain. And so the moral of the story is if you go talk to scientists, and this is definitely my experience, especially when I came to state, and everyone was like, go get grant money. And I was like, okay, let me go get grant money. I run around to other scientists. I'm like, I'm good at math. And they're like, well, we got a lot of measurements. What can you do with it? I'm like, that doesn't fit my math. And they were like, go away. And I was like, oh, fair. So that's what really kind of got me thinking about and getting excited about mathematical methods that really are agnostic about the particular dynamical system or even really needing a particular model. Now, does that mean modeling is a bad thing or going away? No, we need to model all the time. And if we can help it, model from first physical principles. We learn a lot from doing that. However, for example, when Jay walked into my office and said, I want to do a PhD, and I'm like, great. What's your data set that you're interested in? He's like, ionospheric data. I'm like, cool, let's think about doing different kinds of physical models. And then he was like, cool. And he handed me a 900-page book. And he was like, you probably have to read all of this. And I was like, I'm not going to do that. And he's like, well, then we got to do something different than first principles modeling. Right? The moral of the story is that a lot of people over the last 50 or 60 years have spent a lot of time developing very, very sophisticated physics-based numerical simulations for all kinds of different things. And they're great and they do wonderful things. However, we can oftentimes go gather measurements far more readily and far faster than the modeling can keep up with. And as you get into all things related to engineering, right, every time you want that 1% improvement on something, you're going to do 10% more work, right? And you just end up in this death spiral of, for example, if you want to improve, right, physics-based ionospheric models, you're talking about hundreds of thousands of lines of code probably, right, that you are going to tweak. And then how are you going to tweak it? Well, how much electromagnetohydrodynamics do you know, for example, right? So the moral of the story is you kind of start running into this sort of barrier of either you just need to be this hyper specialist in this one thing and that's all you do and that's all you'll ever do, or you kind of have to take a step back and be like, okay, but what if we just measure? People measure all the time. What can I do with just measurement, right? And can I get around, right? Because that's the other thing. If I have measurements, I don't need, right, to go get a better physical model if I can just work with the measurements directly, right? I'll get the model I need from the measurements I have, right? Hopefully, that's the goal, right? So that's really all of the drive here is here's measurements. You don't know what dynamical system it necessarily comes from. You don't have a ready model at hand to explain the measurements. What can you do with it anyway? And can you do anything useful? And thankfully the answer is yes, otherwise I wouldn't be sitting here talking to you, right? A very dreary talk. No, not at all. No, we can't. And piggybacking off of that idea, you can start extrapolating into more and more questions. For example, right, we know in measured data, especially coming from physical problems, right, you're only getting information at the scales that your measurements can resolve, right? And especially if you come from a fluids background, we have the lurking beast that is turbulence, right? And what makes turbulence turbulence? Well, more than anything, what makes turbulence turbulence is that you have a plethora of scales, usually 4 or 5 powers of 10 that you need to keep track of simultaneously, right, to actually explain what's going on in front of you. Even developing measurement devices that can cross that many scales was a major technological achievement realized in experimental fluid dynamics over the last 50 to 60 years, give or take. Interesting factoid, at least as I best understand it, Kolmogorov came up with his statistical theory of turbulence in the early 40s. I think it's called Kolmogorov 41 specifically because it was about 1941. And the only way they could test it at first, and this was done in the mid-50s, there is a bay in Alaska. And for whatever reason, the tidal dynamics at that particular bay are so massive, there's so much volumetric change in fluid, and fluid moves so fast, the only way they could measure Kolmogorov's theory was to get a boat, take it to that bay as it was going through a tidal fluctuation, and stick some kind of pressure sensor off the back of it, and just drag it as all this water just went cattywampus all over the place. And that was the only place that you could actually find, right, experimental conditions that, would actually be sufficient to test the theory. Now they can do it in laboratories, but at the time, right, like even having devices, right, that would be convenient to use, that was a problem because you have so many different scales you're trying to resolve. So, moral of story, we can talk about trying to build models from data alone, but we also then have to start thinking about what happens, right, if you have missing information in your data. What if your data is just limited in the number of scales that you resolve? What if there are things going smaller or going faster and you just can't measure that? It gets averaged out effectively, right, per your measurement device. What do you do about that? And how do you build data-driven models that take that into account in a somewhat self-consistent way? And then probably the more exciting thing, and the thing that's really been the focus of my group, and I think pretty much the center of Jay's life over the last year and a half. Have I ruined your life? Okay, so I've been ruining your life with this for about 2 years now. So we have some ways mathematically to set up, right, inferring dynamical system models from data. But up to the last couple of years, they've all been a little guess and checky, right? And so it became kind of obvious to people, and we definitely piggybacked off some previous work that have really been pushing it forward in our own terms since then. If all this machine learning brouhaha is worth anything, it should be providing rich enough representations of models that we can then hopefully fit to data in clever ways and effectively learn dynamical systems from data alone. And that's really been the big push for us. And we've pleasantly gotten somewhere with it. Incidentally, as you can tell from my rambling style, obviously interrupting me is fine. Don't have some master plan up here that I'm working from. Right? And again, it's all in-house, right? Like I'm not some visiting dignitary. You have to be like, oh God, what will he think if I asked it? Like, it doesn't matter. Right? So ask away. Somebody will, just wait a second. Anyway, so how are we going to build our models from data alone? And we are going to follow in another trend that has been running rampant throughout the dynamical systems community that is now just affectionately referred to as Coopmania. Or everything is linear if you write it that way. And you'll see what I mean in 1 second. So it is actually clever, but there's a way in which you can just look at it and be like, come on, that works. So the idea is the following. Okay, so suppose we do have some dynamical system. I don't know what it is, but it's out there, right? And I think it's responsible for generating data. Okay. Now, with dynamical systems, we have, right, affiliated with them, a flow map, say 5R T, X, and that's just what propagates me forward from my initial condition, right? So I run T and I trace out a path, and that's my solution to my differential equation relative to that particular, right, initial condition. I mean, this is all so high level, it really shouldn't be hideously useful. However, Bernard Koopman in 1931, in an attempt to try and turn all of nonlinear dynamics into a linear theory so that it became like quantum mechanics. He was on some weird stuff at the time. Him and von Neumann were going crazy. Says, well, look, sure, you have your nonlinear system and you have your flow map, and that's all well and good. However, if you give me some observable, say g of x, something you would want to track along the flow, yeah? I can introduce this operator, kt, which we're going to call the Koopman operator in honor of Bernard Koopman. And kt is just g following the flow. That's it. Nothing up this sleeve, nothing up this one. But funny enough, when you write it that way, kt, regardless of the underlying dynamical system, is itself a linear operator. Nonlinear dynamical system, but in this clever little rewriting, in some sense, everything is linear if you write it that way, yeah, you suddenly have a linear representation of a nonlinear problem. Okay. And so dutifully, Koopman, coming from the background of quantum mechanics that he did, and everyone else who's come since then, because this is just what you would do, you say, oh, well, if I have a linear operator, then the first thing I want to find, in fact, the only thing I care about pretty much from that point on, are its eigenfunctions and eigenvalues, right? Because if I have a complete spectral decomposition of a linear operator, then I know everything about it, right? Period. Moreover, right, hypothetically, this is a hopefully categorically easier problem. It's not to solve than my original differential equation. That part didn't hash out, but there's a bit of a workaround. We'll see it here in a second. But anyway, moral of story then, I should be able to take any observable, say G, write it in terms of this basis of eigenfunctions, and then every observable tracking the flow is nothing more than just linear combinations of my eigenfunctions and eigenvalues pushed forward in time. That's it. So all of nonlinear dynamics suddenly collapses onto a linear representation, which it has no business doing. And to be fair, once you start peeling back the details, it's a little more complicated than that, right? So, I mean, on the one hand, yeah, we want to say that, okay, there, nonlinear dynamics is done as a subject. Neat, go home, go study something else, you're done, right? No. Right, so the big point here, and where this gets complicated, right? Observables now come from function spaces. And for us, the sort of canonical one will just be L2 of what I will call observables. And that just means that with respect to at least some reasonable measure, right, the absolute value of this squared and then integrated doesn't blow up, right? So L2 as you usually think of it. But this means immediately that your Koopman operator, no matter the size of your underlying dynamical system, is an inherently infinite dimensional object, right? You've traded finite dimensional nonlinear dynamical systems for an infinite dimensional linear representation. You had to pay a price, and that price is the size of your space just got quite a bit bigger, infinitely bigger, in fact. You can really see this, and we'll have need of this idea of an infinitesimal generator affiliated with the Koopman operator. And if you come from physics, this is really just a long ramble around what we would call the Liouville equation, right? But if we look at the infinitesimal generator, which roughly speaking is just the thing that if we multiply by time and then exponentiate will get us back our k here, right? That looks like the following partial differential operator. Again, F is your original dynamical system, right? Gradient is gradient. And so if you want to find eigenvectors and eigenvalues affiliated with your Koopman operator, that really comes down to solving a partial differential equation. And PDEs are inherently infinite dimensional creatures, not finite dimensional. Now, sure, right, your PDE is linear, that is technically true, but it's a non-constant coefficient problem. And once you start playing with non-constant coefficient problems and nonlinear problems are more or less the same thing, right? All the complications that come up with nonlinearity come up with non-constant coefficients. You can usually duck around a couple of issues, but not that many. So in some ways, as beautiful as this is and as compelling as it is, on the face of it, it's a little doubtful how useful, right, it ultimately is going to be. But go figure. This is where dynamic mode decomposition comes in, and the figures here to keep in mind are Igor Mezek, a la about 2005. He's in the mechanical engineering department at UC Santa Barbara, and then Peter Schmid, who's bounced around a couple of places, but his seminal paper is about 2009, and I think he's at Imperial now. But again, he wanders. So directly, the Koopman representation is maybe not, it's compelling, it's theoretically interesting, but actually getting at it is kind of like, well, how are you going to do that, except in toy problems? But it turns out the minute you start thinking about data, saying, okay, so here we have our time series again, right? Again, it's multidimensional, and I assume that my time series is coming in time intervals of delta t. So just like boop, 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 right? If nothing else, just think about it as you have some continuous trajectory for some dynamical system and you just discretized it, right? Just sampling in some finite number of steps. And y1 is just our initial condition, just a time notation. So, okay, maybe we don't have a model, maybe we have no idea what dynamical system this is coming from, but if we think it's coming from a dynamical system, which is not a radical assumption, right? Then that does mean there is some affiliated Koopman operator, k delta t, that will get me from the jth time step to the j+1 time step. It's got to do that. That's its job, right? Incidentally, because we're going to start rambling about observables quite a bit here, tacitly when we set things up this way, the observables we're using are just a coordinate projection. It's not so important just a second. I didn't put it in because the notation would be gross, but. So what this motivates then is taking my time series and breaking it up into two pieces. Times 1 to nt, and then all those, right, times that are one ahead, right? One step further by way of the Koopman operator. And then we say, okay, oh, that should be no, apologies. Let's find a matrix K that gets me from all my prior times to the next times. And that linear regression has any business working is ridiculous, but seminal papers have been written. True story. Okay. And it does kind of work. And so the idea also here is that you get a nice closed form representation for your matrix K that does this fitting. And it's just y plus times the pseudo inverse of y minus. And then we say, okay, fine. Let K naught be an approximation to K delta T. And then everything I want to know about K delta T, in particular, spectral decomposition in terms of eigenfunctions and eigenvectors, I get from just doing an eigenvector eigenvalue decomposition on K naught. Okay. And again, you didn't have any model beforehand. You just had a time series. And now you've got a model that you can actually use in lieu of, right, just saying, here's the time series. I can measure it at different times. I can generate new data from this if I want, if it's accurate.
So this is the same as the idea of the Carfini log expansion, trying to generate samples of a random vector and the autocorrelation of that random process.
No, it's not. They are kind of cousins in a sense. But what's interesting about this is that I really can go back and say, okay, iterating this should generate time dynamics. This really does give me a whole model to not only regenerate the time series, but ostensibly even go out and do prediction. Whereas Carhoon and Louvre is more of a taxonomic description, right? Flip side, Carhoon and Louvre, right, does a better job of actually addressing, right, the data that you have in front of you from a statistical point of view. This is really kind of a hope and a prayer. I really hope this works. And in relatively simple problems, it really does, actually. Yeah.
You have an idea of how good is the approximation? I mean, I guess it depends on the number of samples you have.
Sure.
And something right. Is there any result that characterize?
Yeah, they're kinda. In terms of like a good numerical like error analysis, no. The best people can do right now, at least that I'm aware of, Jay, maybe you have some thoughts to clarify here, but if I can say that I'm on, right, an attractor in a dynamical system such that my dynamics is ergodic, and that has technical blah, 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 blah. Let's just say we all know what that means for just the sake of argument. If I have ergodic dynamics, then I do know that in some sense, if I resolve down to sort of arbitrary sample time / have an arbitrary number of samples, then I will fully represent the Koopman operator in the infinite limit. But in terms of actually saying your error should look like this for this degree of discretization, I don't think anyone's been able to hash that out. So it's a very experimental science. Jay probably has some feelings about that. I would expect. Right? But again, this is always needs to be balanced against, yeah, this has problems, of course, and there's issues, of course. But when you look at the problem domains where people are trying to use this, it's not like those problem domains are squeaky clean and there's just all the simulation power you could ever want with all of the resolved physics you could ever hope to find, et cetera, right? We're trying to take this out where things get muddy, right? That's the whole idea. So it's going to be a little rough. And sure enough, if you take DMD out in the raw, so to speak, so this is just a classic harmonic oscillator. And then the linear limit, standard DMD is fine, as you'd kind of expect. And so long as nonlinearity isn't too dramatic, it hangs in there like a champ. Off data alone, that's not bad. Until we get near the separatrices where things get dramatically more nonlinear in your model, and then kind of all hell breaks loose, right? That it's even a bounded approximation at that point is nice, right? But it's obviously not doing any good. So, I mean, on the one hand, it's a pretty bold thing to ask for modeling power from just measurement alone, especially with nonlinear time series. Flip side, the most naive implementations of DMD will only get you so far before they just break catastrophically. And this speaks to your point, Jerome. Who knows how much computing power, memory, and resources we would need to actually resolve this. And we'd probably get so swamped by round-off errors along the way that it just would be pointless. Right? It may not even work in finite precision environments. So this gets us to sort of the next generation of DMD, and this is extended dynamic mode decomposition. And the idea here is we're basically saying, well, okay, we're trying to move through function spaces, i.e. collections of observables, right? And we have a lot of literature from numerics that says, well, if you're going to start doing approximation in function spaces, you should be thoughtful about what functions you're using to build your fundamental approximations with, right? And so extended dynamic mode decomposition is really just DMD coupled with a Colloquium approximation. So to wit, now let's suppose that our class of observables we're interested in hopefully lives in some reasonable or close to finite dimensional subspace, right? That can be well described by some family of observables psi sub L. And I have n sub 0 observables or NO as a number of observables, right? Really like to be clever with my subindex. Oh man, so glad. I have a funny slide coming and I can kind of see y'all drifting off a little bit. And the funny slide is like coming right at the, it is just coming like a hawk. Anyway, you got to think about this on Friday evening, right? Like you have to be thoughtful about this. So the idea is we can well explain or well represent the observables we're interested in linear combinations of some chosen subset of observables. And then from there, we introduce our Koopman operator and follow all the natural consequences that come from that. And then the idea is that our finite dimensional approximation is going to be that linear operator that carries us from one time to the next. And then moral of story, once we set that up, we go pick that finite dimensional operator to solve an equivalent, right, optimization problem, effectively identical to the one, right, that I showed you before, but now in a more general setting, because I've introduced these arbitrary observables, right, that I apply to my data that I hope are better representing the function spaces that I want to look in. Okay. And along the way, of course, we're not perfect. We have some degree of error we need to keep track of. And I'm mostly just putting that there as a placeholder for later notation when we get to the true rise of the machines. Now, extended dynamic mode decomposition was put forward about 2015, 2016, and it was very, very promising. Again, keep in mind, 2015, 2016, none of this is desperately old. It's all still pretty fresh. Papers are getting churned out as we speak. Moral of story, what people figured out all of a year later, basically in the literature, was how you pick your observables radically affects the approximation you get, and you better pick right, otherwise you can get complete noise, just garbage. And it can be very, very hard to tell what's good from what's bad. And that's when people took a step back and said, well, okay, there's this rising world of neural nets. Obviously, these two things need to talk to each other. Please tell me this is the funny slide. Yes! Like, it's so funny on like so many different levels, right? You would take a TI-84 to represent a Terminator, which is supposed to be an artificial intelligence. Like, I love it. Like, I live for that kind of humor. Anyway, hopefully most of you are old enough to even know the reference. So, right, we summon in machines, we bring in neural nets, and this is really where Jay has shined over the last couple of years. I was like, Jay, I don't want to read the TensorFlow API, you do that. And he did, and mastered it, and he's been doing all kinds of wonderful good things with it. So what's the idea? So instead of picking observables by hand or saying, I think they should be our mean polynomials or they should be trigonometric functions or whatever, we say no. We're going to introduce a neural network, script E there, that's going to take us from whatever space we start in sub S, and take us to the number of observables we want or think we need. And that is a hyperparameter that we have to pick, and we'll talk about that here in a second. Okay. And incidentally, our layer or neural nets are about 4 layers deep by 128 neurons long, so they are deep. Okay. And we're hoping that this is going to give us a far, far richer space of observables to work with. But more than that, right, observables we will find, right, through some optimization routine. So hypothetically, observables that will ultimately get picked out, right, that best work with the data that we feed in, hopefully without overfitting, of course, right? Always the problem, right, when you do these sorts of things, that right, bias variance battle, which is the real Monarchian dilemma, right, of the modern world. It's not good and evil anymore, it's bias and variance. Just letting you know that. Anyway, so we have a forward neural net that takes us from in sub S to our number of observables, and then we introduce a reverse neural net that takes us from our number of observables back to our original coordinate system, right? So we're really thinking of E generically as embedding up into some what we call latent space of variables or embedded variables. And it's there actually that we're going to do all of our DMD, right, in the transformed coordinates. And then once we're done, we have D that brings us home. And so the relationship between D and E is just that it should ultimately give me something like an identity. Okay. And at this point, we're technically obliged to say something about like, yes, this is an autoencoder, sort of. We don't exactly use it like that. And the point here is that autoencoders are usually done in such a way that you're going from high dimensional data down to low and finding some fundamental pattern, right, that would otherwise be hidden from you in, right, the sea of too many dimensions. And we're actually kind of going the other way. We're starting in relatively low dimensions and kind of trying to figure out what higher dimensional space do I need to embed my dynamics in to get good representations of it by way of the DMD algorithm. Okay. And I can say that, and it sounds semi-coherent, but really you have to see it, and then you'll get what I'm fussing about. Yeah.
great. I'm kind of getting a little bit stuck, but tell me if I'm thinking about this wrong. So what you're saying is, based on stuff that was talked about before, train to learn the right model, you need the right measurements. To get the right measurements, you need to learn the right model.
No. So I see what you're saying. I see the circularity there.
It's like the Henry in the bucket. There's a hole in the bucket.
Yeah.
You need something to fix the hole.
Yeah.
And then you need to put, or get some hay, and then there's fire, and then there's this, and then it comes back to like, to put out the fire, you need the bucket.
Yeah.
And then there's a hole in the bucket.
Yeah. And I mean, they're probably, to some extent, that dilemma for what you're trying to do is probably on some basic level unavoidable, right? You pay a price for your ignorance. And one of the big pushes in sort of the areas that I've been working in is how do you get more physics in here if you have physics to put in, right? I mean, anything you can do to pre-guide this in some reasonable and sane way you should be doing. Because otherwise, yeah, in some sense, you're kind of chasing your own tail a little bit. More innocently, right, it's just a more sophisticated way to do that regression at the end of the day, right? It's still ultimately, though, just saying, I have a time series here, I look one step ahead, and I want to fit it, right, with some linear fit. Because I think that's a good idea because Koopman said so. We didn't even actually say it in 1931, but I hope we would have said it, right? Now that said, we do a little more than that when we train. And this is where it actually gets downright clever. And this is what took us a long time to wrap our heads around. Now, part of our loss function, which ultimately guides the training here, is very straightforward, right? We said D and E need to give me an identity, so it better do that, right? That's the first term, right? That's just ensuring that if I go into my transport coordinates, D will bring me back, right? Fine. The second term, my DMD loss, is just that one step, right, error, right, from my regression, right? I want to go one time step ahead with a linear matrix. I fit with a regression. That's the error that comes with that regression. Fine, right? But then the clever bit, and this is really Jay's doing after much experimentation and fussing and studying what other people have done, was saying, yeah, but that's not enough. You need something else that says, hey, look, you want to use your linear model as a time stepper. We're not just doing Cahoon and loop. We're not just doing PCA. I'm actually recreating dynamics. I am building effectively a representation of my dynamical system such as it is. And as I do that, I need to make sure every time step I run it forward and come back to my original coordinates, it's where it should be. And so what we kind of stumbled on, I don't think we thought about this at first, but once we had it, we were like, oh, it's one step accuracy coupled with a global stability constraint. And one step consistency and stability gets me convergence. And so in some sense, we kind of figured out a way to do this where, right, it's kind of working like a canonical time stepper, right, should in the theory of ODEs, or numerical ODEs, right? And once we put all that together, we were like, oh, okay. One, we got to make a really nice diagram and put that in the paper. That pleased me to no end. I don't think I expressed how much that, maybe I did, I don't know. I was in a really good mood. I shared the paper with some colleagues and they're like, that's a nice figure. And I'm like, damn right it is. Right? So aside from the nice figure, which is basically saying, right, we have an analytic way where this is really the full Koopman operator that takes us from one time step to the next. This is truth. And we have an approximation scheme that says embed, do DMD, come back down, and that should hopefully get us pretty close. Oh, and then there's some regularization details, standard kind of machine learning stuff. It's nominally boilerplate in there too. If you want to know the details, don't ask. I'm management now. It's nice. So let's go back to that harmonic oscillator where our standard DMD algorithm failed. Not completely, but right, once we started getting out towards the separations, things got rough, right? No, not so rough. So in this case, we can actually get away with a number of observables that's identical to the actual like space that we're working in. So our autoencoder in this case is a diffeomorphism. Now what's neat is that this is what happens in the original coordinates. And this is what happens, right, to our trajectories when we embed them. And so you can see what the autoencoder, such as it is trying to do is kind of get that nonlinearity and chill it out. You still have elliptical orbits, obviously, but they're nowhere near as pronounced, right? And so the autoencoder is kind of trying to say like, oh, what you would really like to do your DMD algorithm is something that looks a lot more like linear dynamics. So let me help you find that, right? That's what it's doing. I mean, that's what the optimizer is doing. We, to our credit, and compared to some other groups that are doing similar work, we don't put a lot of assumptions into the way that we train. It's pretty naive, actually. And so this is really just what the machine decides to do. Now, that's really not all that shocking. What kind of blew my mind and still tickles me to no end is, and then I said, okay, because I kind of wanted to explore two-dimensional phase space geometry, right? So, okay, harmonic oscillator, one center. Duffing equation, two centers, right? With a saddle separatrix, right? Separating the regions. What does that do? And it turns out when we tried to just use a diffeomorphism so that the number of observables, right, or the dimension of our embedded space was the same as the underlying physical dimension, that was okay, but not good enough. Not that good, actually. But by giving it one more degree of freedom to embed into, and you can see this in the embedded coordinates, right? It's like, oh, okay, that separatrix, I'm just gonna, boop. And now everything got smoother, easier, tidier. And you can still see it kind of trying to, roughly speaking, completely linearize the flow, but it also has enough room to move that it can tell that it has different regions to deal with, but it's lifted that separatrix, that saddle in such a way, right, that it's dealing with everything smoothly, right? Which is what allows it, and again, what we're seeing here with the DLDMD is tests, right, not trained tests. So roughly speaking, it's predicting, right, trajectories it didn't otherwise know. So our machine really is acting, right, as a full realization, right, of the underlying dynamical system. That plot still just super, super tickles me. And if you know anything about like the Tokens embedding, you know, literature, that kind of thing, this isn't exactly that, but it's very much in that vein of thinking. And so it kind of, I don't know, it, incidentally, there's a paper by a very famous person in dynamical systems, Barbanel, from '92. And it's one of these long review papers, like 65, 70 pages long. And towards the end of it, he has this whole section on, and he kind of even phrases this, where he's like, neural nets are these new things. It's like 1992. He's like, neural nets are these new things. They don't really work. But if they did, here's what I would use them for in dynamical systems. And it took from 92 to basically the present day, and now there's this whole slew of papers coming out where they're basically going, oh yeah, we can make that work now. And that's kind of what's going on, and it's cool. Like, it's really cool. It's like there's this whole part of dynamical systems theory that was difficult to turn into computational, right, algorithms that neural nets hypothetically could actually like get us there. I mean, it's slick. What an exciting time to be alive, in a positive sense for once. Anyway, and then I said, okay, so we've done Hamiltonian problems. Let's do Vanderpool. Vanderpool was nasty. But I mean, you can even look at it, like we cranked up the nonlinearity. So this is a more dramatic version of Vanderpool, right? and a globally attractive limit cycle. And the thing about van der Pol that really seemed to throw the machine, and you'll note we need a lot more embedded dimensions here than what we start with. And the next natural question is, well, how do you know to pick that? And that was guess and check. And we're trying to figure out ways to make that a more systematic, right, thing that we explore. But for now, guess and check got us there. Thankfully, it didn't need 253. Anyway, what's the problem? We can kind of see, right? Van der Pol really has, aside from just the dramatic nonlinearity of the limit cycle, and we're clearly moving to a kind of singular limit here, right? That's one of the issues. The other is you have that, right, unstable spiral. So everything from the interior is growth, and your, right, dynamic mode decomposition needs to predict growth, which is to say unbounded eigenvalues, roughly speaking. But everything on the outside is collapse. So everything in is trying to grow, everything out is trying to decay. So that right there tells you at a minimum you need 4 dimensions, because I just need 2 different complex conjugate pairs, right, to get the job done. Now, what we didn't realize, we started with that and we were like, oh shit, that wasn't good enough. So, right, like the nonlinearity itself demands yet more. Now, what's intriguing is, I mean, obviously trying to plot an 8-dimensional embedded coordinate is a little beyond, unless we wanted to start putting things in the water, right? But we were playing around with it, Jay plotted a bunch of curves and like, man, they all look basically sinusoidal. He's like, well, let's do FFTs and see what they look like. And what's intriguing is when you look at the coordinates in embedded space affiliated with this, they're nearly monochromatic. So when our machine linearizes in the embedded space, it really is finding things like fundamental modes. And it's like, oh, van der Pol needs 8 of these nonlinear but linear kind of fundamental modes to well describe the dynamics and do prediction. Which is cool. I don't know what it means. And again, as with so many things in machine learning, right, we get the result and we're like, hey! And someone's like, why? And I'm like, so I am, as I said at the beginning, I put way too much in this talk. So the second part, also involving Jay, is gonna go by probably a little quick. My apologies. And no, this isn't one of those things where you can just give me 5 more minutes. Like I just missed this.
So you were gonna say January 6th.
What's that?
It says in January, I give another talk.
Yeah, I probably, yeah. Well, then there's the whole stuff with the ionospheric data that we actually got to work, and that just merits its own talk altogether. I thought I could squeeze it in and do this cool like 3, but no. Yeah. Questions? I'm about to completely change subjects, so, oh, yeah.
Sure, for the dumping equation, you have,
Yeah.
I don't know the mathematical term for it, but some sort of critical point in which you transition from orbiting a single center to orbiting 2.
I forget exactly how dumping works. We've got the saddle in the middle, right? Center. And then there are exterior orbits. Yeah, if my energy is high enough, right? I just go around both.
Right. Okay.
Yeah.
So call it whatever you want, critical point in energy barrier. Does the behavior of the process or expansion degrade when you get close to that? I mean, it seems to be wanting to make it into ellipses,
Yeah.
pairs of ellipses, right?
Yeah. Yeah, and so that it definitely, like, anywhere where the orbits are going to get sharper, more nonlinear, et cetera, yeah, like that's where it's going to struggle the most. That's where it's spending most of its time learning. And when you actually look at like our learning curves and how much error is dropping epoch by epoch, like the softer you can make everything, the radically faster you can train. So it's spending all of its energy really trying to figure out how do you work around these things. So yeah.
But at some point, you can't. There's a transition. It's like
Well, no. But that's the point, right? Is that in some sense, by giving yourself these extra dimensions to move through, it's giving it other paths then to explore. I don't have a better answer right now than that kind of hand wavy sort of thing, but that generally seems to be the way it's behaving. So it lets it kind of look around regions, you know what I mean? And that's how it's able to smooth things out.
Do you get any analytic expressions out of this? I mean,
Here and there.
can you write down an equation for at least a harmonic oscillator or as a result of what you do?
Sure. Kind of. I mean, relative to what we have with our machine, no. Flip side, in some sense, we're kind of saying, once I've trained this machine though, and we all believe that it's doing what it's supposed to do, then I would just give it to you and you would run it, and that would be your harmonic oscillator prediction machine for all time to come.
No, but if I'm trying to learn the model, the terms, and what matters.
So that in some sense, so there's a couple of different answers to your question. One, and this gets to some of what Jerome was asking about, you can, over relatively simple problems, and the harmonic oscillator is kind of one of the last horizons where you can do this because it's an integrable, right, model. You can kind of do the whole full DMD Koopman representation analytically. You can sketch all of that out. It's some work for sure, but you can do it. That's one way to answer your question. Another way to answer your question is what you're asking for also is a little more like model.
Can I help the model?
Yeah. So for us, the model is the machine. Now, what you want is something a little more like what, for example, one group called SIND, SIND lowercase y. And they're trying to do, I mean, what they basically do is suppose that they have like a dictionary of functional terms. So polynomials, trig terms, and then anything else they want to throw in there. And they say, here's my data, right? Be it low dimensional or high, right? And then I'm going to use a machine to do the fit, right? And figure out what terms matter over here for the data that I have. And then that will be literally my model, right? For this data. And this will give me my dynamical system. So people are absolutely doing that, for sure. We're not going in that direction just this second. Unless a reviewer decides to really throw a fit with us, and then we will. Yeah.
Two questions.
Yeah.
The second one is related to the first.
Sure.
This idea of projecting the data in an higher dimensional space
Yeah.
and come back.
Yeah.
That seems very similar to the philosophy of the super vector machine.
What's that?
The super vector machine. SDSU.
Oh, okay. Yeah.
So that's basically what they are doing. Projecting a higher dimensional space.
Yeah.
That now the samples are way more separated and it's easier to put hyperplane, separate and classify. So it's sort of a similar kind of philosophy, not exactly the same way, but
Yeah. So the thing with the support vector machines, and again, like I still feel like a relative noob in machine learning. And I bring that up because the feeling I get when I listen to the older, bigger kids on the playground in this is that SVMs were beloved in the 90s and into the early aughts because they are easy to implement, easy to explain, mathematical theory abounds, but they're effectively linear approximators, like you're saying, hyperplane fitters, basically. So, you know, at best, you're kind of doing some like slick convex optimization problems, right? But when you want to take them over nonlinear problems where nonlinearity is real, and that is the case here, then you got an issue.
eventually see the SVM as a particular case of that.
That's an interesting question, and I don't have a yes/no answer to that. And that might actually be a really elegant way. I mean, because yeah, you're trying to put things in a linear context by way of the Koopman operator. That could be slick. I don't know. We should talk about that.
My second question is about that N0.
Yeah.
You have any clues how you should choose that N0? I mean, based on the given problem?
Nope. No, and like, let me tell you how bad this is. So I'll just confess, like, this is how bad it is. My mouth. Anyway, so Duffing 3 worked, and we were like, oh, okay, cool, that makes sense. And then I looked at Vanderpool, I was like, it's gotta be 4. And Jay came back, it's like, it's not 4. It's 8. And I was like, okay, well, I'm glad you were able to figure that out by literally going 4, 5, 6, 7, 8, and then finally 8 like made you happy. And that didn't take years. And then, you know, so we submitted to Chaos, the journal, and someone said, well, the journal's called Chaos, give us a chaotic dynamical system, basically, in the reviews. And we were like, well, fair. And so we dutifully run out and grab Lorenz 63, because it's the smallest continuous time chaotic dynamical system, and we all know everything about, you know, stand a chance of doing something with it. And I thought Jay was going to come back and be like, I had to do it in 9 dimensions, or 10, or 11, or 12. You got away with 4, right? So Vanderpool wanted 8, Lorenz 63, arguably a categorically more complicated problem, is cool with 4. Fine. Fine. I don't know.
Do you think that there is maybe a way from the data themselves that you can guess what should be?
I really hope so. And when Mason Porter was here, that feels like that should be some kind of basic question in topological data analysis, right? That there is something about my data that when I project it into one coordinate number of dimensions versus another, you feel like there's got to be some fundamental topological feature that is either clearly getting blown up or created or whatever. And that should give you that clear, like, because it's not a continuous perturbation. Changing dimension is not smooth, right? So something should get triggered along the way. And I brought that up to him and his eyes lit up and he was all bouncy and like, that's a great question. You should go talk to, what is her name? Elizabeth, Michigan State. She's extraordinarily good. I've unfortunately forgotten her last name. I can find it. But anyway, moral story, he's like, go talk to the other kid on the playground who knows all about this. But it's an absolutely open question. And what's interesting is I brought up Tokens embeddings. Tokens embeddings go back to 1981, and enormous amounts of literature have been written about you should do this and you should do that. And it turns out all of it was just elaborate guessing. None of it consistently works. So there's problems in dynamical systems and how we do data analysis by way of dynamical systems that have been lurking around for generations, that are begging for the same treatment. So it's not just us, is what I'm saying. Maybe.
Yeah, I also have 2 things to explain. Continuation of features question. It doesn't mean model writing means like a linear, quadratic, or what kind of model. In any dynamical system, when you develop a model, there is always a parameters that plays some rules. Can you have some sense of parameter you can extract from your method?
I mean, the cheap answer is we can just dump the weights in front of you of our neural net. That's not going to make you happy. And in some sense, Joe has been writing his master's thesis with me on how do we actually wrap our heads around the weights that are coming out. And does that have information that we can actually glean some insight from? If for no other reason, just to understand when are we training well, or when do we need more embeddals, or when are we training poorly? But then hypothetically also hopefully be able to answer something from a more applied point of view. Right now, the game in town for what you want to do is very similar to what Peter was asking for, though. Is that the thing with the Cindy stuff is that they also put sparsity promotion into their algorithm. So they're really trying to drive things down to here is the most parsimonious number of parameters, right, for your data set, for the model that we're going to tell you is useful. Now, last caveat on that, all of this is bleeding edge. Whether or not we should be saying anything about your real world models where people might live or die from them is another matter entirely.
Another technical question.
Yeah.
No matter what observable you take, do you always get that diagonalized matrix? Is there a problem? VT, inverse diagonal? No
That's what
problem
we,
at all?
what's that? That's what we want.
Okay, you pick observable in such a way that you get.
Yeah, that's what we want.
So,
Yes.
so I understand from before that we are still have to adopt a certain delta t in order to do the Koopman.
That's right. Yeah.
So in a practical way of view of this thing, what is better when you are doing this kind of learning of the dynamic system? try to increase the dimension of your NS, or try to increase the resolution of your, let's say, system?
That's a really good question. In some sense, I don't think we ever really looked at, in some sense, the kind of underlying error analysis that lower resolutions would get us versus higher ones. Now, it is worth pointing out, the embeddability question is a little more fundamental than even just resolution. Like, all the resolution in the world didn't make this ever go better, because you just have this fundamental problem of 2 is not enough, you need more.
But on the other hand, you can have a lot of NS, but a very poor resolution, and you anyway want solve the problem.
Yeah, right. Yeah, so right now, we were just amazed we could even get the thing to run. So we're still kind of on that, just like, oh my God, right? The more refined kind of analysis that you're talking about needs to be done, and it will get done, but we haven't done it yet. Yeah, all the trade-offs, and what about this, and what about that?
But here you are choosing a certain delta T.
We're choosing a certain delta T that we know is going to make it go.
Okay.
Yeah, for sure.
Just a comment on all of these systems, there does seem to be some sort of ceiling to the number of embedded dimensions.
Okay.
And at some point, all of them fall apart.
Okay.
Adding 100 dimensions to any one of these, like you can't just arbitrarily keep tacking on dimensions. For some reason, 8 and 3 and 2 are just magic numbers. Why that is?
No. More. Oh, Stefan.
Never mind.
Do you have a question? Or?
Yeah, on the, I have a couple. What's your CPUs? I mean, in other words, what's the machine architecture, RAM, and how long does it take to actually finish training and stuff like that?
Jay.
So it's written in TensorFlow, it trains on the GPU, and it takes an hour.
Okay.
Although, just as a quick side note, like, Jay really did a lot of amazing work where it was like 8 to 10 hours, and then it was 5, and then it was kind of 2, and now it's down. So Jay really has like ruthlessly cut that down. Yeah, that's great. Yeah.
I have a question about when you're training these, implicitly you're still doing an inference problem, which means that all the terms in the real dynamical system that may exist behind or active through the process of getting the data is what you implicitly capture.
Roughly speaking, yeah.
So if wrong with the dynamical system, non-equilibrium columns and complex situations like we are, is that you're eventually going to have some other terms that will activate that were not present in the original.
Yeah.
That's not going to get captured.
Yeah.
The question is, have you thought or estimated how much would you have to pay on the resolution that you're going to lose if you suddenly say, I'm going to train my data that I have,
Yeah.
and I'm going to add artificially terms that I know that may exist eventually. And I'm going to do it. The problem is, the more terms you add, you're kind of going to lose resolution on the actual system that is active. And because the fun thing is to be able to say when I'm going to be out of what I have trained, because that's what the future looks like. Otherwise, you just have systems that you expect to be periodic or regular for a certain extent.
So the one way I can answer that, we haven't really systematically explored that, and that's a really good question. If it weren't already time, I would be getting to the second part of my talk.
Yeah, but I think that
Yeah. We'll talk again. But anyway, moral of the story, we have thought about the question of, for example, say I have slow and fast dimensions. And in some sense, this is kind of what you're getting at. And let's say I only have measurement on slow, not fast. How do I do DMD then? And we have worked through that. There's still a lot to be done in that, and we basically just like kicked ass on toy problems. But there is a way in which hypothetically all of this starts to become a closed loop. So we can start going in that direction. I mean, for us, it's going to be toy problem by toy problem by toy problem. But, and it's 4:35. So what's that?
That will be the next one.
That will be the next.
so we're gonna thank our speakers.